right, so what we're looking at today is we're in the energy unit and we're doing the second page of the salmon colored notes. Second page of the salmon colored notes is what we're doing today. And it deals with energy, heat and temperature. All right. So, start things off here. I have a flask filled with water. And I'm going to take the temperature of the flask with this thing right here. So I take the temperature of the water, and the temperature of the water is 20 degrees Celsius. All right. Next, I'm going to take these two beakers. One of them I'm going to fill 100 milliliters of water. We'll call that beaker A. And then the other one we're going to fill with 50 milliliters of water. We'll call that beaker B. And I put them on the hot plate. And we're going to heat them up. Going to heat those up for 2 minutes. Okay. Going to heat those up for 2 minutes. Now, with the hot plate, both beakers are located, at pretty much the same location on the hot plate, so they have the same number of coils and stuff underneath it. So the point being is that both of those beakers should be getting the same amount of energy from that hot plate. All right, so we're about a minute in, so we got about a minute more here. All right, so it has been 2 minutes. All right, so I'm going to take 2 beakers off the hot plate. Going to take the temperature first of the 50 milliliter one, and the temperature is 52 degrees. The temperature of this one is 41 degrees. So 52, and 41. So this one went up 11 degrees, this one went up, went up 21 degrees, this one went up 32 degrees. All right. Now, if I were to ask you which one of these two has more heat, what people frequently say is B has more heat because it has a higher temperature. Right? But in actuality, they both got the same amount of heat because where they're getting their heat from is from the hot plate, and they're both on the hot plate for the exact same amount of time, and the hot plate's giving off a steady flow of heat. And if they're both on it for the same amount of time, they both got the same amount of energy. What's different about them is with this one, the 100 milliliter beaker, there's more molecules of water in there. So the amount of energy that each molecule got was less. Here, again, it got the same amount of energy, but it had a lot fewer molecules than that one did. And as a result, each molecule got more energy. And that's why the temperature went up more in this one because each molecule got more energy. Again, they both got the same amount of heat, but this got more heat per molecule because there were fewer molecules. Well, that's basically the difference between heat and temperature. Heat is basically the amount of energy that it's getting, where temperature is the average amount of energy per molecule. All right. So the analogy I like to use is, let's say that I'm driving to work, I played a scratch off, and I won $200. And because I'm a swell guy, I decided to give $100 each to two of my classes. Now, one of the classes has 25 kids in it. The other class had 14 kids in it. All right. Well, if I give each class $100, 100 divided by 25, in that class, each kid would only get $4. Where the other class was 14 kids in it, 100 divided by 14 works out to be about $7. So each kid in that class would get $7. Now I gave each class the same amount of money, but there was less money per student in the class that had more students in it. All right. Same idea here. So something like a swimming pool, if I raise the temperature of a swimming pool 1 degree, that takes a tremendous amount of energy. It takes a tremendous amount of heat to do that because there's so many molecules in a swimming pool. So it takes a tremendous amount of heat to do that. Whereas making a beaker of water go up 1 degree, it doesn't take nearly that much heat to do that because there's a lot less molecules in here to heat up. So heat's the amount of energy, temperature is the amount of energy per molecule. Now the unit that we use to measure heat is called a joule. In this class, it's called a joule. There's more than one unit to measure heat. One you may be more familiar with is a calorie. When you look on the side of your box of cereal and it tells you how many calories there are in the food, what it's actually measuring is how much heat energy there is in the food. They take the food and they burn it and they measure how much heat comes off of it. That's how they figure out the calories in it. So calories is another unit of heat, but that's not the unit we're going to use in this class. We're going to be using joules in this class. All right. For temperature, different units for temperature. You got Fahrenheit, Celsius, and Kelvin. In this class, we're primarily going to be using Kelvin or Celsius. We don't use Fahrenheit too much. All right, so that's heat and temperature. Now, there's different ways in which heat moves from one place to another, and we call those the methods of heat transfer. And an easy way to remember these methods of heat transfer is to match them up with some form of cooking. Because when you cook food, you have to use one of these methods of heat transfer to cook the food. Right? So the first method of heat transfer, conduction. Right? So imagine a big cast iron frying pan, handle like that, and I put that big cast iron frying pan over the fire. Now, I put it over the fire, what's going to happen is it's going to heat up the frying pan over here, but also that handle on the frying pan is going to get hot as well, right? So if you're going to grab it, you'd want to use like an oven mitt or something like that. All right, so if the heat source, the fire is over here, how does it get to the handle over here? Well, it travels through the cast iron through the process of conduction. And what happens in conduction is molecules collide with each other. Right? Molecules are moving. Molecules are moving. When things are cold, they move slowly and they only move a little bit. When you heat something up, molecules move faster and they move more around. All right? So what happens here is, over here where the fire is, the molecules start moving quite a bit, and it starts banging into these guys, and these guys start moving. It starts banging into these guys, and these guys start moving, and it starts banging into these guys, and these guys start moving. And it's kind of like a chain reaction, goes all the way down the line there. So the analogy I like to use for this is dominoes. The analogy I like to use here is dominoes. Imagine as each domino as being a molecule, and these are the molecules that are in the frying pan. All right. Well, what happens is, if something that happens over here and this guy moves, that movement, they bang into each other and that movement works all the way down the line there. All right. Now, so it's basically what's kind of happening through there. Right. Now, conduction takes place best in solids, and the reason why it takes place best in solids is with solids, molecules are very close together. So if one of them starts moving, it's very easy for another one to start to get collided with and start moving as well. With gases, for example, the molecules are really far apart. So that would be like if I'm setting up the dominoes and I move the dominoes this far apart, right? If I knock over this one, it can't collide into the other ones because it's too far away from them. That's basically what happens in gases and to a lesser extent liquids. The molecules are a lot farther apart, so if one of them starts moving, it's probably not going to bang into another one. Now, some materials, even with them being solid, some solids are better conductors of heat than other solids. Typically, the things that are better conductors of heat are things that are more dense. So like metals, like iron or lead, things like that that are very dense, the molecules are much closer together, so they bang into each other much easier. Something like styrofoam, even though it's a solid, styrofoam, the molecules are farther apart, so they don't bang into each other as easily. So that's why heat doesn't conduct very well through styrofoam, and why they use styrofoam for insulation, because the molecules are farther apart, they don't bang into each other very easily. All right, so that's conduction. All right, so if you cook something in a frying pan like that, you're going to be cooking by conduction. Okay. Next up, convection. All right. Convection, unequal heating results in different densities within a material. The hot, less dense rises while the cold, more dense sinks. So let's say that I have a beaker like that. And with that beaker, I put a heat source underneath it, right over here. Now what's going to happen? The heat source is going to heat the water. It's located right there. All right. Now, when I heat up the water, what happens is the water expands, and when the water expands, it becomes less dense. And when it becomes less dense, what's going to happen is that water there is going to rise, because less dense stuff rises. Now, if that water moves upward, something has to come in and take its place. So it's going to be water from the side is going to come in and take its place, like that. Now, this water rises because it's less dense and warmer, but now it's moving away from the heat source. So what's going to happen to this water is it's going to start to cool down, but it can't just turn around and start falling back like this because the water underneath it's rising up. So it kind of gets pushed off to the side over here. And again, it's getting even farther away from the heat source over here. So it's going to cool down, become more dense. And when it becomes more dense, it sinks. And it replaces this water that moved over there. So I end up with this circular movement of water like this, where it's going to rise above the heat source because it's less dense, and it's going to sink away from the heat source because it's more dense. And this is called a convection cell. This is called a convection cell, a convection current. And what this does is it spreads heat throughout that whole container of water. Right? So if you're cooking something like pasta, you're going to make macaroni and cheese, and you had to boil the macaroni. When you put it in the water, the movement of the water is going to be like that, and it spreads the heat throughout it. Now, let's say I move the heat source. Let's say I move the heat source to over here. Well, now over here is where it's going to warm up, and over here it's going to become less dense. So it's going to rise over there. The water over here comes in to take its place. This water kind of gets pushed off the side, cools down, becomes more dense. So now it's a convection current, but because the heat source is on the other way, it's going to circle that way. All right. Now, let's say that I do it so that I put the heat source in the middle. All right, so again, right above the heat source is where it's going to rise, like that. Over here by the sides of the container is going to be where it's cooler. So what I end up with now, instead of one big convection current, I'm going to have two small convection currents. And sometimes if you're like cooking rice or something like that, you can actually see the grains of rice kind of going around in circles because they're following the convection currents. Okay. So it rises above the heat source because it's less dense. It sinks away from the heat source because it's cooler and more dense. All right. So I'll show you an example of that. Got this device right here, this contraption. So going to light the candle here. All right, so I'm putting the heat source right over here. All right. And what else I'm going to do is put a nice white back so you can see this a little bit better. All right, I'm going to put some food coloring in here so you can see how the movement of the water is. So you see the food coloring is going down like that. It's going over to where the heat source is. And now you can see that the dye is going up right there, right? Because right here is where the heat source is. So it's heating the water right there. It's becoming less dense. So it's rising right here. And it's going around, and then it's going to cool down, and then it's going to start sinking again. So the movement of water is going around like that, where it's rising above the heat source and sinking away from the heat source. I could add a little bit more food coloring, a different color in there. So you can see that it's still going on. So again, it's going down there. It's going across the bottom there. And now it's going up like that. Right, so again, it's circling around like that, up above the heat source and down away from the heat source. All right, so that's convection. That's convection. Okay, third method of heat transfer, radiation. Electromagnetic energy that can travel through space. All right, so electromagnetic energy would be things like infrared energy, visible energy, ultraviolet energy, stuff like that. How does that go with cooking? All right, well, let's say that I have here is a cross section of a toaster. There's little heating coils inside the toaster. So you flick on your toaster. What you'll notice is those little heating coils, electricity runs through them and makes them glowing red, so they get really hot. All right. Now, I drop a piece of bread in there, and the heat goes from the heating coils to the bread, toasting the bread. But you gotta think about, how is that bread getting the energy from the heating coils, right? The bread is not physically touching the heating coil, right? If the bread was touching the heating coil and the two solids are meeting each other, it could be conduction. But typically your bread doesn't touch the heating coils. If it does, it burns. Right? So it's not by conduction because it's not touching each other, right? Now there is air in the toaster, but it's not really heating the bread by convection either, because in convection the heat rises. So here's the heating coil. It's going to heat the air right there, and then air is going to rise up. So what's happening is the coil is radiating energy. It's radiating infrared energy, and then the piece of bread is absorbing that radiation, and that's what's toasting the piece of bread. So toasters cook things by radiation. All right. Another thing, right? If you're at like a campfire and you put like a hot dog at the end of a stick, and you put the hot dog near the fire, how that's going to be cooking is primarily by radiation as well. If you have a radiator in your house, and you feel the heat coming off that's radiation. With this hot plate, all right, if I had this plugged in and I had my hands over here and I feel the heat coming off of it, that's radiation. Now, one thing about radiation that makes it special from these other two is with conduction, it takes place in solids, because in solids, the molecules are close together. Convection takes place best in liquids and gases. And the reason why it takes place best in liquids and gases is because liquids and gases can move very easily. There are some solids that can move, like ice can move, but it moves very slowly. So it takes place better in liquids and gases. Radiation can travel through empty space. So that's how we're able to get energy from the sun, is by means of radiation. So the sun gives off energy. Those waves, energy waves, travel through space and they get to the Earth's surface and they heat up things on the Earth's surface. So that's where most of the energy at the Earth's surface comes from, is from radiation from the sun. Now, good absorbers of radiation are also good radiators of it. So something like this black in color, when radiation hits it, it absorbs that energy very easily. So like black colored things heat up faster than white colored things because the black color absorbs that radiation more. So a good absorber is also a good radiator. What that means is if it takes in the energy, it takes in the radiation very easily, it also loses that energy very easily as well. Right? And we actually do a lab where we'll look at that in a lot more detail. All right, so conduction, convection, or radiation are three methods of heat transfer. All right, so let's say we look at a few like food items. All right, a few food items here. All right, scrambled eggs. So between conduction, convection, and radiation, scrambled eggs, you can typically cook those in a frying pan. So the eggs are physically coming in contact with the iron in the frying pan. So it's traveling by conduction because it's a solid. All right. Rice. How you cook rice is you put rice in boiling water, and in the boiling water it moves the moving unequal heating of the water moves the energy around, and it cooks the rice. So rice, because you boil in water, would be convection. Baking a cake. All right, so you bake it in an oven. Most ovens are convection ovens. They heat up the interior of the stove there, the oven, and it's designed in a way where the hot air rises and the cooler air sinks. So most ovens are convection ovens. If I'm preparing a bagel, all right, what I do is I slice the bagel in half, and then I take the bagel and I put it in a toaster. So a bagel would be an example of something that's being cooked by radiation or toasted by radiation. A pancake, again, with pancakes, you're going to be using a frying pan for that, so that would be conduction. Right? So whenever you're cooking something, you're using a method of heat transfer. So that's an easy way to, whenever you cook something, just kind of think about, okay, how's the heat getting to my food? All right, so that's methods of heat transfer.